When the seismometers registered the 5.6 off the coast of Vancouver Island, most people who felt the tremor went back to what they were doing within minutes. A 5.6 is not unusual for this region. The Pacific Northwest sits on one of the most seismically active margins on Earth, and small to moderate quakes ripple through the crust there with a regularity that locals have long learned to live alongside. But the scientists watching those seismometers did not go back to what they were doing, because to understand a 5.6 off Vancouver Island is not to understand one earthquake. It is to understand its context. And the context, in 2026, is something that the scientific community has been watching, with an intensity that has measurably increased over the last 12 months. Beneath the floor of the Pacific Ocean off the coast of Vancouver Island, something is happening that has never been directly observed before. Not on this fault. Not on any fault. In September 2025, a study published in Science Advances based on data gathered during a 41-day expedition at sea aboard the research vessel RAV Marcus G. Langseth produced what researchers described as the first clear images ever captured of a subduction zone actively tearing itself apart in real time. Not breaking suddenly, not rupturing in a single catastrophic event, tearing slowly, section by section, like a train derailing one car at a time, in a process so new to science that the geological community does not yet have a complete vocabulary to describe what happens next. And directly above those tearing plates, cities sit, roads run, schools and hospitals and bridges have been built to standards that are still being debated. And 326 years have passed since the last time the fault above the tear let go completely. The Cascadia Subduction Zone is a fault system stretching approximately 700 miles along the Pacific coast of North America, running from the northern tip of California through Oregon and Washington and up to British Columbia. It marks the boundary where two oceanic tectonic plates, the Juan de Fuca plate and the Explorer plate, are slowly sliding beneath the North American plate at a rate of roughly 4 centimeters per year. That motion sounds gentle. It is not. Subduction zones are the engines of the most powerful earthquakes ever recorded. They are responsible for the 1960 Chilean earthquake, which at magnitude 9.5 remains the largest earthquake in recorded history. They produced the 2004 Indian Ocean earthquake and tsunami, which killed over 230,000 people across 14 countries. They produced the 2011 Tohoku earthquake and tsunami in Japan, which reached magnitude 9. And one generated waves up to 40 meters high and caused the Fukushima nuclear disaster. Every one of those events happened at a subduction zone. Cascadia is a subduction zone. It is, according to the Oregon Department of Emergency Management, a fault capable of producing megathrust earthquakes of magnitude 9, 0 or greater. Scientists currently predict there's approximately a 37% chance that a megathrust earthquake of magnitude 7, 1 or greater, will occur in the Cascadia Subduction Zone within the next 50 years. And the last time it fully ruptured was January 26th, 1700, known precisely because the tsunami that event generated struck the coast of Japan that night and was recorded in Japanese historical documents. The earthquake itself was estimated at magnitude 9, 0. The coastline of the Pacific Northwest dropped several feet in the hours after it struck. The Great Cascadia Megathrust happens roughly every 400 to 500 years. As of 2026, it has been 326 years since the last one. This is the geological context in which every earthquake off Vancouver Island must be understood. Not as an isolated tremor on an isolated fault, but as one more data point in the slow, inexorable accumulation of stress on a system that has failed catastrophically before and will fail catastrophically again. What the September 2025 Science Advances paper revealed has added a new dimension to that understanding, and it is one that the geological community is still working through in real time. The study was led by Brandon Shuck, an assistant professor at Louisiana State University who specializes in marine geophysics, working with data collected during the NSF-funded 2021 Cascadia Seismic Imaging Experiment, known as CASI-21. The team used seismic reflection imaging, essentially an ultrasound of the Earth's interior, sending sound waves from the research ship into the seafloor and recording the echoes with a 15-kilometer-long streamer of underwater listening devices trailing behind the vessel. The resulting images resolved the structure of the subducting plate at a resolution that no previous survey of this region had achieved, and what they revealed in those images stopped the team. The northern section of the Cascadia Subduction Zone, the portion off Vancouver Island where the Juan de Fuca and Explorer plates meet at a system of faults called the Nootka Fault Zone, is tearing apart, not as a metaphor. Literally, physically, measurably tearing. The seismic profiles show a vertical drop of approximately 5 kilometers, roughly 3 miles, where part of the slab has shifted downward relative to its surroundings. A fault has sliced through the oceanic crust at this location, and it is actively separating. Along roughly 75 kilometers of this fault, The data show alternating sections of active movement and seismic silence. The active sections still building stress, the silent ones marking regions where the slab has already partially detached and is no longer accumulating the strain that produces earthquakes in the way a locked fault does. Schuck described the process in terms that capture its scale without losing its precision. Getting a subduction zone started, he said, is like trying to push a train uphill. It takes a huge effort, but once it is moving, it is like the train racing downhill, impossible to stop. Ending it requires something dramatic, basically a train wreck. What the CASI 21 data shows is that the train wreck is happening, not all at once, not in an hour or a decade or even a century. In geological time, slowly, in fragments, section by section, the northern Cascadia margin is unraveling. A microplate is peeling away from the larger Juan de Fuca plate. The subduction engine in that section is losing power. The system is dying. For millions of years, geologists have found evidence of this process in ancient rock formations, the remnants of previous subduction zones that ended, leaving behind small fragments of oceanic plate called microplates embedded in continental crust. They understood those fragments as the product of this kind of gradual plate separation. What they had never had was a living example, a subduction zone caught in the act, a fault photographed in the process of shutting down. Cascadia, off the coast of Vancouver Island, is now that example, the first of its kind ever directly observed. The immediate question that the discovery raised in the minds of everyone who read the paper, and in the minds of the public that read about it, was, does this mean the danger is lower? Does a subduction zone that is tearing itself apart, one that is in the process of shutting down, represent less risk than one that is fully operational? The answer, stated clearly and directly by the researchers, and by the April 2026 Conversation article that addressed this specifically, is no. The tear is happening in the northern section of the Cascadia margin, the area off Vancouver Island where the Explorer plate meets the Juan de Fuca plate. This is not the section of Cascadia most geologists have identified as the greatest immediate hazard. The central and southern sections of Cascadia, the portion running offshore from central Oregon and Washington, are still fully locked. Locked means that the two plates are stuck against each other, not sliding smoothly past, but held in place by friction while the forces that drive the plates continue to build. Every year that passes without a rupture adds more strain to those locked sections. The strain does not disappear. It accumulates. And when the fault finally slips, when the locked sections release, the stored energy becomes the earthquake. As the April 2026 Conversation article stated directly, parts of the Cascadia boundary remain strongly locked, meaning that strain is still building and could be released in future large earthquakes. A tear in the plate may influence where ruptures start and stop, or how far they propagate, but it does not remove the underlying seismic hazard. The subduction zone is not shutting down fast enough, and not in the right sections, to reduce the risk to the Pacific Northwest on any timescale that matters to the people living there now. What the tear does change is the scientific understanding of how a future Cascadia megathrust might behave. The tears and fractures visible in the CASI 21 seismic profiles create structural complexity in the subducting plate that was not in any previous model of Cascadia's fault geometry. Scientists are now studying whether a major rupture could jump across one of these tiers, propagating from one section of the fault to another across a structural discontinuity, or whether the breaks might instead act as barriers, stopping a rupture from spreading as far as it might otherwise travel. This distinction matters enormously for how long a future earthquake lasts, how much energy it releases in total, and which coastal communities experience the most severe shaking and the highest tsunami waves. The honest answer, as of the current state of research, is that scientists do not yet know which way it will go. The new structural data has improved the resolution of the hazard model without settling the most important practical questions about how a future earthquake will behave. It has given scientists a sharper picture of the problem while making the problem itself more complex. The 1700 Cascadia earthquake is known to scientists not just from Japanese tsunami records, but from evidence written into the landscape of the Pacific Northwest itself in ways that anyone can see if they know what to look for. On a site in Oregon called the Neskowin Ghost Forest, the trunks of trees stand dead in the surf. Sitka spruce and western red cedar that were killed when the coastline suddenly dropped several feet as the fault slipped and the ground subsided beneath them. They have been standing in that surf for 326 years, preserved by the cold Pacific water, their roots still in the soil they were growing in when the earthquake struck. Dendrochronology. The reading of tree rings has dated the year of their death to between 1699 and 1700. Similar ghost forests exist along the coast of Washington and Oregon. Cores taken from coastal marshes across the region contain a distinctive stratigraphy, a layer of soil suddenly replaced by marine sediment at a consistent depth across dozens of sites, marking the moment when the coast dropped and the sea covered what had been dry land. That same boundary layer, when radiocarbon dated, consistently returns dates clustering around January of 1700. The earthquake is in the soil. It is in the trees. It is in the Japanese historical records of a tsunami that arrived without warning on a coast thousands of miles from its source. And it is in the geophysical models that use all of this evidence to reconstruct what happened and to project what will happen again. The January 26th, 1700 earthquake was estimated at magnitude 9. 0. It generated a tsunami that inundated coastal areas of the Pacific Northwest and crossed the Pacific in hours. Geological evidence suggests the coastline in some areas dropped by 1 to 2 meters instantaneously. Modern modeling of a comparable event, a full margin Cascadia rupture in 2026, projects tsunami waves reaching coastal Oregon and Washington communities within 15 to 30 minutes of the earthquake, in areas that are home to tens of thousands of people and that are separated from high ground by flat coastal plains with limited evacuation routes. British Columbia's own risk assessment, the Disaster and Climate Risk and Resilience Assessment published in October 2025, describes a full Cascadia megathrust earthquake as currently one of the more likely extreme earthquake scenarios in the province. The annual probability of the extreme event is assessed at less than 1%, but that probability rises to between 2 and 10% over the next 10 to 30 years. The probabilistic math on a 400 to 500 year recurrence interval, 326 years after the last event, is not subtle. The new data from the CASI 21 expedition has also clarified something about the seismic behavior of the northern Cascadia margin that geologists had noted but not fully understood. The Nootka Fault Zone, the transform system that separates the Explorer and Juan de Fuca plates, and within which the tear has now been imaged, has historically produced earthquake patterns different from the rest of the Cascadia margin. The fault produces regular small and moderate earthquakes, including events in the 5, 0 to 6.0 magnitude range, of the kind that prompted this story. Before the CASI 21 study, the pattern of those earthquakes, the way they clustered in some sections and went quiet in others, was noted but not explained with precision. The new imaging provides the structural explanation. The active earthquake sections correspond to regions where the fault is still moving, still accumulating stress in the conventional subduction mode, while the quiet sections correspond to regions where the slab has already partially detached and is no longer building stress in the same way. This means that the moderate earthquakes off Vancouver Island, the 5.0s and 5.6s and occasional 6, the zeros that register on seismometers and send brief ripples through coastal communities, are not random background noise. They are, in the interpretation of the KSI 21 team, a direct expression of the structural complexity now imaged in the plate beneath them. Every moderate earthquake along the northern Cascadia margin is occurring against the backdrop of a fault that is simultaneously tearing itself apart geologically and capable of producing a magnitude 9. 0 megathrust earthquake catastrophically. These two things are not contradictory. They are happening on different timescales. The tear on the scale of millions of years, the megathrust hazard on the scale of centuries, and they are occurring in different sections of the same fault system. A moderate earthquake off Vancouver Island in 2026 could be on the tearing section, or it could be on the locked section. And the locked section is where the energy is building. What is happening at the practical level in the emergency management offices and engineering departments and municipal governments of British Columbia and Washington and Oregon reflects the unresolved tension between what the new science knows and what preparation requires. The 2024 BC Building Code that came into effect in March 2025 has updated seismic standards for new construction. But the built environment of the Pacific Northwest carries the legacy of decades of buildings constructed to lower standards. In Victoria and Vancouver, heritage buildings of unreinforced brick, some of them in the densest parts of the city center, are among the most vulnerable structures in a major earthquake scenario. Schools built in the 1960s and 1970s exist on soil that liquefaction modeling predicts will behave like a liquid in the seconds of strong ground shaking that a Cascadia megathrust would produce. The British Columbia DCRRA of October 2025 does not soften this picture. It acknowledges directly that a full Cascadia megathrust earthquake remains one of the province's most significant hazard scenarios, and that the building stock, the infrastructure, and the public preparedness level are not yet where they need to be for an event of this magnitude. The document does not set a timeline on the earthquake. Nobody can set a timeline on it. The Cascadia fault does not operate on a schedule that human institutions can plan around with certainty. What it operates on is the physics of accumulated strain, and the physics, as of 2026, suggests that the balance sheet of energy stored in the locked sections of the fault is significantly positive. Brandon Shucks, the lead author of the Science Advances study, stood on the deck of the RV Marcus G. Langseth during the Cassie 21 expedition in 2021 and listened to sound waves bounce back from 3 miles beneath the ocean floor. The data those sound waves returned, processed, and analyzed over the following years produced the first clear image of a subduction zone actively breaking apart. He described what they found with a precision that reflects both the scientific significance and the human stakes. The Earth is splitting open beneath the Pacific Northwest, he said, and scientists are watching it in real time. They are watching it because every piece of structural information about the fault is a piece of information that goes into the models used to project where the shaking will be strongest, which coastlines will be hit first by the tsunami, which parts of the fault will rupture and which might not. They are watching it because the 1700 earthquake is in the soil and in the trees and in the Japanese historical record. And the next one is in the locked sections of the plate, in the strain accumulating at 4 centimeters per year, in the math of a fault that ruptures every 400 to 500 years, and has not ruptured for 326. A 5.6 off Vancouver Island does not, by itself, tell us when the next great Cascadia earthquake will happen. It is not a foreshock in any sense that current seismology can confirm in advance. It is a reminder that the system is alive, that the plates are moving, that the stress is building, that the fault is not sleeping but simply waiting. And it is occurring above a section of plate that, for the first time in the history of geology, has been photographed in the act of tearing itself apart. 3 miles beneath the ocean floor, in a process that began millions of years ago, and will end in a rupture that the people living above it will feel in the soles of their feet before they hear it coming. The scientists watching the seismometers are watching because they know what the ground is holding. And they are watching because when it finally lets go, the difference between 15 minutes of warning and no warning at all is the difference between tens of thousands of lives saved and tens of thousands lost. They are watching because the ground beneath Vancouver Island has a history, and that history is not finished.